Okay, hello Tallinn. Good to see you everyone at Latitude59, and we're kicking off one of the most deep tech sessions of this conference about quantum computing and the marvels of it. So I'm Benjamin, I'm a venture partner at Luna Ventures, which is an early stage deep tech venture capital fund, and over the past 2 years I've been interviewing over 100 computing startups for my blog, which is aptly named Future of Computing. So today I have the pleasure to record the first ever podcast episode with Sebastian Weidt, founder and CEO of Universal Quantum, as my podcast guest. So Sebastian, welcome.
Hi Benjamin, great to be here. Thanks for having me.
Let's kick it off with a quick intro. So I've already told you who I am. Who are you and what are you up to?
Yeah, hey, like you said, my name's Sebastian. I'm co-founder and CEO of Universal Quantum. I'm also a professor in quantum computing and entrepreneurship. And yeah, I love building quantum computers. That's really what we do at Universal Quantum, and love to explore that with you further.
Sounds awesome. Let's take it from a pretty high-level perspective, and you could be doing many things in life that are exciting. So why quantum computing? What's the story? How did you get into this?
Yeah, great question. I've said this sort of publicly before. I don't have the story of, when I was 5 years old, I started dreaming about quantum. Not the case at all. But I think I've always been really passionate about, working on things that have impact. And I've always wanted to be involved in something that can really move the needle for society. And I think I used to think, go straight into business. That's where you can do that. But I did a degree in physics and thought I'd go back into business. Did for a little while, did some management consulting, but then did a PhD in quantum and started to get exposure to quantum computing and realized that it's not just a sort of academic topic alone, but that there will be commercial applications down the line. And I think if you think of it in terms of impact, it'll be very difficult for anything to easily beat quantum computing in the long term in terms of impact. And that excited me a lot. I was very, very lucky throughout my sort of academic journey in working on things that really gave me a lot of confidence that what we were developing could be turned into a very useful technology, could really move the needle for quantum computing. And so I carried on, and I think when you look at quantum computing, you really want to build that sort of technology at scale. You've got to do this in business. I think that's really what you, in our view at least, what you need to be pushing into. And for me, that was obviously a nice sort of circle complete. I could go back into business, use the sort of skills I've acquired, the knowledge I had on quantum, and push that into the market.
Was there any particular moment or event that really triggered you to go for quantum rather than any of the other exciting computing trends that we see recently?
I don't think, again, coming back to the impact side and also my sort of personal passion and love for quantum, I think combined makes it a pretty appealing sort of story for me and reason for pushing this forward. I think just kind of reiterating, on the computing side, that's why there isn't really much that can have the sort of impact that quantum computing will have in the medium to long term. And I love quantum. So what better ways than combining those?
Nice. Let's explore this a bit further. So I guess many of you have heard quantum computing as a buzzword and might have some very vague idea of what this might be and have heard of weird quantum effects and whatnot. So what is quantum computing?
Yeah, so quantum computing is a new technology focusing on solving really difficult problems. And this may be a surprise to some of you, but there's a huge range of problems that we currently can't solve, even with the most powerful supercomputers and AI and whatnot out there. We have no way of solving those problems. And quantum computers, for certain applications, are really good at tackling those sort of problems. So, it's not about making conventional computing, just keeping computing Moore's law alive for a while. It's really doing things that you could spend 1 million years on a classical computer. A quantum computer will be able to solve in a reasonable time scale. It's that step change that this technology will enable. In terms of how it then works at a high level, so we introduced the concept of these qubits, quantum bits, analogous to your bits in a classical computer. These Quantum bits, they store the information. Here we can store information as a 1 or a 0, just like you will find in a classical bit. But because we live in this quantum world, so to speak, these qubits can be 1 and 0 at the same time, which adds some really nice functionality, so to speak. Now, why can this qubit do that? When we talk about quantum computers, we obviously have to very much talk about the quantum part of it. And when we look at quantum, we usually deal with the very, very small. So if you zoom into the desk you may be sitting in front of, if you go onto the atomic scale, everything that happens there is governed by what's called quantum mechanics or quantum physics. And in this quantum world, really weird things happen all the time. So for example, an atom can be in 2 places at the same time. We get this strange entanglement, that we can talk about later, or conveniently skip it because it's pretty mind-boggling and complicated. But what quantum computers do is they use these quantum phenomena in a very nice way to actually compute information in quite a revolutionary way.
Now, in terms of actually practically building a quantum computer, we're seeing all these different approaches out there where companies are exploring different types of qubits, like superconducting qubits, ion traps, but also photonic qubits, silicon spin qubits, whatnot. Like, there's so many qubits out there. Why are you going with ion traps? Why do you think that's the way forward to build a practically useful quantum computer?
Yeah, so you're introducing a lot of different things there. So in quantum computing, there's many ways of building these machines, and like you said, you just Google it and you're immediately confused, blown away, and have no idea what's really going on, because there's different ways of building these machines. Coming back to the quantumness of it, we need to find something that experiences these quantum phenomena, and that could be a photon. That can be an atom or a trapped ion, a superconducting qubit, and therefore these machines look quite different when you look at these different platforms. Now, to your question, why do we use trapped ions? It's a multitude of points on that, and I think the first thing we need to ask ourselves: what does a quantum computer actually really need to look like? To give us this utility, unlock these great applications that we often associate to this technology. And I think when you look at it from that lens, then one thing you very quickly realize is that you need a quantum computer which has many of these qubits, these quantum bits. They need to be very high quality, and you need to be able to control them really, really well at scale. And I think when you then use that lens or that filter and apply that to the different technology approaches out there, what we have found is that trapped ions tick many of these boxes. So I think at the moment, if you look at the best performing quantum computers out there, they really come out of in my opinion, the trapped ion space. It's one of the best performing qubits out there. But usually what people would refer to is that, or point to, is that the trapped ion platform struggles to scale. Just like many others, actually, there's this huge problem of, how do we go from the sort of machines that we have today, which, by the way, are, somewhat useless. They don't really solve huge problems just yet. They're great toys. They're great for engagement, to learn more about quantum, to develop applications. But we can't yet use these machines to solve these really hard problems. And for that, we need to scale up. And just to kind of put this into context, right now, the sort of best quantum computers out there, tens of qubits, maybe 100 qubits, we need to push towards that sort of million qubit scale eventually. So how do you do that? And I think that's where people often don't have very good answers, apart from pretty pictures on a roadmap. And I think what we have focused on for many, many years is to find a way to open up this route to scaling up for the trapped ion platform, because it's fundamentally a really nice platform. And this is really what we have managed to do, and why I stayed in this field and very passionately driving this in the business arena now, because we really believe we have that way to scale up quantum computers. Sorry, long-winded answer there, but just to kind of give you an overview.
No, this is actually great as we're exploring and learning more about your technology. And now as you're building these quantum computers, what is sort of your North Star metric that you're optimizing for and that guides your development?
Yeah, it's interesting, right? Often people will talk about fidelities, so the quality of the qubits, the quality of quantum gate, which is an indication of how well you can process information in the end, how many qubits they have, and so on. But fundamentally, if you look at where we are today and the sort of road ahead to get to these larger scale systems, I think often people don't really talk about a metric around how well can a system scale. And that's because it's actually really hard to come up with a metric. And I'm not going to sit here right now and tell you that I have one. But I think you therefore really need to dive into the technology approach to get a good understanding of what the roadblocks may be for scaling up. Now, one of the things that I can metricize to some extent is when you think about a large-scale quantum computer, by and large, and I think that there's broad agreement in the sector on that, it has to be a modular approach. And what I mean by modular approach is if you really take those two words literally, then what I would argue is that each module, each chip, call it a quantum chip, needs to act as a sort of mini quantum computer. And what you then need to be able to do is plug these things together to make bigger quantum computers. Now, it turns out in the classical world that this is not so bad, right? We have multi-core, classical computing chips. That's kind of the way it worked out there. In quantum computing, it's incredibly hard to connect quantum chips, quantum modules together in a quantum way. It is something people often don't really like to talk about because they don't have very good answers on that. And I think it's really one of the key questions on how to scale up. Now, we fortunately found a way there, and not so long ago, maybe a year ago or so, published this I think rather remarkable paper where we demonstrated a link between two quantum modules, which is as pure as it gets. I think we had around 7-9 fidelities. For anyone who doesn't know what that means, it's a near perfect link, which you never really find in quantum. It just doesn't really normally work out that way, and it's incredibly fast. So we've managed to open up this really nice window of opportunity to scale up our technology through that what we call UQ Connect, in terms of then really being able to scale up significantly.
Which is really a big deal, as many people are looking into connecting quantum computers, possibly adding another platform like some photonics to get these interconnects right. And having that out of the box with very high fidelity, that sounds amazing. So,
yeah, just to add to that, just so people get an understanding of the whole landscape. So we're talking, there's a couple, when we talk about connecting within quantum computing, there's really two regimes that I would point to. There's one where you're connecting quantum chips or quantum modules within a quantum computer, and photonic interconnects is something people often point to, and they don't really work yet. And then there's the sort of connection that one day is required to connect different quantum computers across the globe, right? And we're getting into the sort of quantum internet type vision, and how does one do that? And I think there actually the photon it plays a crucial role. I think if you want to connect a quantum computer here from beautiful Estonia to London, use a photon. That's a good way of doing that. But I think given the challenges with that technology, when you're within a quantum computer where things have to happen very quickly, where the quality matters a lot, we've worked really hard to not have to use those photonic interconnects and instead use our UQ Connect technology. So I think these photonic interconnects are still required, but just to a lesser extent when it comes to connecting different quantum computer to perform some communication function between the two.
To zoom out maybe a little bit, as there are generally, I would say, two schools of thought within quantum computing, where one is like, let's make use of these noisy, error-prone machine, which they call near-term intermediate scale quantum computing, Nisk, and let's see if we could do something useful with it, versus the other school of thought, which is more like we absolutely need to build fault-tolerant, error-corrected quantum computers to eventually do something magical. So where on the spectrum do you guys sit?
Yeah, so let me just explain a couple of things there. So, and sorry to take this back to the fundamentals, but the, quantum computers, so we need quantum systems, so it's something very small. And it is something that we do not experience in our sort of day-to-day life. We can't be in two places at the same time, unfortunately. Now, one of the challenges with quantum and quantum technologies more broadly, is that it's very fragile. You have to work really hard to protect these quantum systems, these qubits in the terms of quantum computing, from the environment. If you don't do that well, it becomes classical. It destroys the quantum nature of it. So when you then look at quantum computers, one of the big challenges is how do you protect these qubits? How do you remove noise from the system to get the quality of qubits up as good as possible? Now, as it turns out, you will never really have a perfect qubit. You will never be able to do this perfectly. I think this is a sort of general understanding now, which means we need to have a way to programmatically, so to speak, remove these errors. And what you do at that point is you implement these error correction protocols. And actually, not that dissimilar to conventional computing, where people often use error correction algorithms to remove errors on the resistor level. So we have quantum error correction algorithms as well. Now, what these algorithms, high level, are saying is give me lots of qubits, and I'll remove these errors for you and give you a smaller number of very pristine, what we would call logical qubits. And that's actually what you would process your information on. Now, that's really where that big goalpost comes from, that we have to push the qubit number up so dramatically. Now, because that is really hard for many, well, for all of us, but I think some may see this as an unsurmountable challenge for their platform, a focus has really gone on to, well, what can we do with the machines that we have today? And this is really where this Nisk era came in, this noisy intermediate scale quantum computers. Hey, we've got some beautiful machines here. Is there anything we can squeeze out of them? And people are doing some remarkable work around the world trying exactly that. I think this is where some of the hype in the field has maybe come from. I don't think it's quite happened as some people may have said, which is unfortunate, but in our mind at least not so surprising. And I think this is why we have always kept that strong focus on scaling up, even if or when we find certain applications with smaller machines. We will always want to have more. We will always want to have faster machines. We will want to unlock the next application. So in our mind, given that our technology allows us to think that way, really focusing on scaling up is the way forward. So we're in that camp, if you want to characterize it that way, the error correction camp. But I'd also say any application that people uncover suited for smaller scale systems, we can obviously tap into that as well on our way to larger scale systems. So for us, you can put us in both camps if you like, but the ultimate goal for us is to go to larger scale systems.
And I guess that's a really crucial point, because if people are throwing around, numbers like we need millions of qubits, it's also a good question, do they mean physical qubits or do they mean logical qubits? And in the end, we'll need millions of both logical and physical qubits to do amazing stuff. Now, the thing for logical qubits and, perfect quantum algorithms is we have mathematical proof. Like, we know that if we get this right, that there will be some computational advantage. While on the other hand, for some of the Nisk stuff, it's more, like alchemy, that we might get it to work, we might get some advantage out of it, but it's not quite clear. And how do you navigate this field in picking, what application to optimize for or to target as you're developing this technology?
Yeah, right. So just to clarify, I think the target of pushing towards millions of qubits, physical qubits, is absolutely there. We hope we don't need millions of logical qubits. I think if you look at some of the toughest challenges out there, be that breaking RSA encryption, is one of the applications that, from a national security point of view, people get worried about in certain areas in government. You need a fair few thousand logical qubits. But it all depends on the quality of those. But I think that's what we're sort of targeting. I think remind me, sorry, of the second part of the question.
And for fault-tolerant quantum computers, we have mathematical proof that they're going to work, right?
Got you.
Well, for Nisk, it's less clear. So how do you navigate this?
Yeah, so it's a great question. I think the way we approach it is that we optimize our machines for error correction. And I think if you look at that, if you can do error correction well, you can. I don't want to make a totalitarian here, but I think you can cover most of the other applications as well. We do keep an eye on that, and there's great work going on by many companies out there, and we're doing some work on that as well to see what can we do in the short term, and that has an impact on our machine. But I think ultimately it's error correction what you need. We're focusing our sort of hardware and lower layer software development on that, and I think programmatically we can tap into sort of Nisk type applications as and when they appear, if that becomes sensible to do so. I think if you look at our hardware approach, it is quite remarkably flexible actually, and I could dive deep on that. I don't want to bore the audience if it's not where you want to go, but there's a lot of flexibility we actually have in terms of how we architected the hardware that would allow us to be quite flexible there.
No, which is actually interesting, especially when you think of chemistry applications, and you might want to gear your quantum computer to the particular, say, molecule that you're simulating and trying to better understand. So how much flexibility do you have to adapt your quantum machine, in real time to the molecule that you like to simulate?
Yeah, I think it depends on the algorithmic ask. So we are not a quantum simulation company. That's a completely different approach. We're really focusing on developing a universal quantum computer. So any algorithm that you develop, we can run on our machine. Now, when it then comes down to, well, how efficiently and how well can you run those algorithms, you would normally start talking about connectivity in your system. So when you run these algorithms, usually what they will ask you to do is have qubits communicate with each other, implement these quantum gates, similar to logic gates in the classical architecture. And so it then becomes the question of, if the algorithm says, hey, I'd like to have qubit number 5 and 2050 to communicate, how do you do that? How do you implement that? And I think that's where connectivity comes in. We have a fully connected quantum computer, which means we can directly make those demands from the algorithm work with very, very little overhead. There's some other architectures out there where the qubits are effectively printed in place. You can't move them, which means if you want to move that information or have these qubits talk from one chip to the other edge of the chip, they have to make some very error-prone operations to get that information there. We can actually, which is quite cool, but we can physically move our qubits in space to take them wherever they need to go to, meet up with a qubit somewhere else on the chip, do their thing, and then they go somewhere else again. And moving these qubits is a remarkably error-free operation. And I think that's where our sort of fully connected system comes from, and therefore we can change that connectivity in the system in software. So if an algorithm demands a different connectivity, we can just program that in. We do not need to change the hardware.
Now, we talked about scalability already, and there's, I guess, always this consideration: how much effort do you put into optimizing the qubit and get the fidelity higher, the error rate lower, versus when's the right time to start adding more qubits and to really go scale this platform? So how are you thinking about that?
Yeah, great question. High fidelity is required. I'm mindful not to go too deep here, but high level, when what the error correction algorithm that we talked about earlier says, hey, give me more qubits and I'll deal with this error problem for you. The sort of total demand that this algorithm will put on the total number of qubits actually comes from the underlying physical fidelity that you have. So the better quality qubit you have, the lower the overall number of physical qubits this algorithm will ask for. And therefore it behooves us, so to speak, to keep on improving our fidelity and do whatever we can there. Now, your question on where when do you switch? When you be like, okay, I've got fidelity, now scale up. Unfortunately, what we're seeing in the field, I think, is that it doesn't quite work that way, because when you look at some of the machines that were built early on, people did beautiful, amazing work in getting those machines to work, and they really focused on, let's say, getting a 5 or 10 qubit machine to just work as perfectly as they can. And the whole engineering approach was to really solve the problem for the 10 qubits. It then turned out, if you then said, well, okay, you've got 10 now, I'd like to have 100, they had to re-engineer the entire thing, which has an impact on the fidelity. And I think it's a great question, actually, the way you post it as well. So therefore, we're looking at this completely differently. We don't think it's wise to just focus all your efforts on getting a couple of qubits to work really, really well, and then be like, okay, and now I just somehow scale this up. It's really, in our mind, take us the other way around. Think very carefully about what a 1 million qubit system needs to look like for your approach, and then work back in terms of what you need to do today. Now, that may mean that you end up front-loading some of the engineering tasks and some of the difficult things that, but show that all works at small qubits, and then you've got a naturally scaling platform. So the quantum computers we're building right now, and we're building a couple for the German government, for example, and in the UK, when you look at those machines, it's basically a unit cell of a 1 million qubit quantum computer. All the core engineering blocks that are needed to make a 1 million qubit machine usable are already integrated into this smaller scale machine. And that's heavy work, that's expensive work, but in our mind it's the way how we can then scale up much, much faster than what we're currently seeing in the field.
Now, speaking of recent trends that we're seeing in the field, there's been different announcements from different players about logical qubits, or at least being able to detect errors and then potentially also correcting for them. So are we seeing a transition from Nisk, that is noisy, to logical, which is like Lisk, where you have actual logical qubits, and we're getting closer to this vision of fault tolerance?
Yeah, it's a great thing we're seeing in the field right now. People starting to play around with error correction, playing around with the sort of early steps of logical qubits. I think I'm not quite with you yet on that segment, so we're almost there. It may sound like it to many people, but it's really, we're seeing the beginnings of a logical qubit. The quality of that logical qubit is still not very, very good, but at least we're showing that the mathematical framework of error correction and so on really does work in practice, and it also allows us to play with these systems now, to do some more learning on it. So it's an important journey that we're going through right now towards that fault tolerance. But again, if you're working with some logical qubits on a 100 physical qubit system, you're still a long way away from a physical hardware perspective to get to these larger scale systems. But it's a really important phase that we're going through right now. That's really nice to see that we're getting into that sort of error correction territory.
Yeah, and a machine that ultimately could do something useful. So as we've been speaking a lot about the technology already, and now transitioning a bit more on the commercial side and all these applications, why we're actually doing this. So now we're making all these, steps and reaching those milestones and developing a quantum computer. And ultimately we want to do something. So what applications are you most excited about that we might reach the first?
They may differ between the two. So I'm very, very passionate about applications in healthcare. I think one of the reasons I and others at University of Quantum, really got involved in this space is to do something really good, something very positive for society. And I think my personal view is when I look at the different applications, what we may be able to do in health is it's just mind-blowing. It's really incredible, and I think that a lot of drive comes from that. But there's many other applications which have huge implications, right? Be that in the security space, material science, finance. It really goes across all major sectors where we're seeing that there will be some really interesting, really exciting applications that will change things quite dramatically, I think. And I think this is why we're seeing, people getting in early, starting to play with these machines, getting quantum ready, so to speak, to start to understand what these machines will be able to do for their business model. It could have a negative or positive impact, right? And that knowledge needs to be acquired because this technology is so different, right? We always advise that you don't sit there and wait until these big machines are there and someone says, hey, I've got an application. For you to then know what to do with that is years of work. Because your normal programming doesn't work in the same way, that the way you frame a problem is completely different. So it's important to engage with this technology in a measured way as we scale up and start to unlock these applications.
Nice. When talking about health, so I guess it's mostly drug development, and how can a quantum computer help with that?
Yeah, it's one area. There's other areas as well in logistics and imaging and so on for scans. So it really actually remarkably goes across the board in the healthcare sector. I think when we think about drug discovery, you look at at the moment it takes around 10 plus years to develop a new drug, right? And part of the problem, there's other problems as well, is that it's very difficult to understand how chemical reactions work. It's difficult to simulate that. So you really have to do a lot of trial and error, put two things together and see what happens. It's very difficult to understand complex molecules using conventional computing. That they don't like these sort of fundamentally quantum problems, if you think about it, right? Everything that happens in a chemical reaction is quantum by nature. Now, it turns out there are already known quantum algorithms that show us that quantum computers will be able to really help in a really nice way with those sort of problems, and thereby hopefully provide a tool to the healthcare sector, the pharmaceutical companies and so on, to develop new drugs better, faster, and so on.
When I think about quantum computing becoming useful, I'm always wondering whether there will be some sort of ChatGPT moment where everyday people can experience the power of quantum computing. Because when I'm thinking of drug development and chemistry more broadly, it will be done probably in-house by some chemical company where some engineers get to deal with quantum computing. But it's something that not everyday people will experience more directly. Is that something you would agree with, or?
Yeah. It's a good question. One I don't have an answer to in terms of do I agree with it or not. I think there's a way to maybe map this ChatGPT moment to quantum, and I think starting to really show the utility of these machines that we will see in the future will be one of those moments. I think in terms of this B2B, B2C type thing, the way, at least high level, that we often look at it is what we're fundamentally doing at Universal Quantum is we give society a tool to do some really awesome things with, right? We're not proposing to develop new drugs ourselves, right? It's you provide this computational resource, to smart people out there in their respective fields to then use that in whichever way they deem best for their sector. So it's this enabling part, which I think is really exciting, because you're going to see this pop up all over the place, right? There will be a new drug that is only there because of quantum, and that's really how it's impacting people. I might not be smart enough yet to foresee how this will impact your sort of, on your phone or whatever, the sort of the general public would want to use on a day-to-day basis. But I think, let's see, the exciting thing that I often point to is that we're still at the beginning of uncovering what quantum will be able to do for society. We already know a huge amount, enough to warrant to get very, very excited about this, and for government and investors and so on to significantly support this. But at the same time, we're still at the beginning. And I think if you look at the journey of conventional computing, no one imagined we would be where we are today, right? We're quite naive, I think, often as a society in thinking about, well, what is something going to change going forward that we haven't seen before. And I think we're going to see something similar in quantum computing as well.
Now, we're here at the Latitude conference talking about quantum computing, doing public outreach, inspiring people for quantum. And what are, some other initiatives that you've seen to get people excited about quantum and actually close this talent gap between what we'll need in the future in terms of quantum engineers working on quantum and what we have today?
Do you mean locally here or?
In general.
In terms of initiatives to drive engagement with the sector? Yeah, I think it's there's a lot going on, right? I think one, and this is where what we've seen with Nisk has been useful, because it's, we're in a stage now where you can go online today and play around with quantum computers, right? And while they may not be able to solve a utility creating problem for you just yet, engaging with that technology is important in many ways. It enables us to funnel in engineers to be quantum engineers, quantum software developers, and so on, as they get excited about the technology, as they can play around with this. So I think that's really important. There's huge government initiatives around the world right now. People often point to there being a quantum race. What is China currently doing with quantum? That can have security implications, and I think so. Therefore, there's a big push on the national level. National centers being set up, a lot of funding being made available. These 2 quantum computers we're selling to Germany are part of that, vision that Germany has for scaling up quantum computing. So I think all of those initiatives are really important to push the sector forward. It's a marathon. It really is, and I think people getting involved with the sector need to be aware of that, which is why I always, quite loudly speak about what is ultimately required, so we don't burn out in the first year or 2 because we thought everything's going to happen in the next couple of years, but really have that sort of longer term view. And I think if we make sure we have that, this is going to be quite transformational for people around.
How do you see progress in quantum computing globally when you compare, say, the US versus the UK and Europe? Well, some of the early larger player has been in the US, but now there's this component ecosystem emerging in Europe, which seems to be quite strong and promising, and which might be a good avenue into building large quantum players ourselves.
Yeah, I'm a huge advocate of us having to do this in Europe as well. One of the great things we're seeing, and especially in the UK, and Germany and France for that matter, is that we've had a really strong academic base in quantum. And if you look at the spin-outs that have been created in quantum technology and quantum computing in particular, that they come out of that really strong academic base. And therefore, I think we've got great diversity and great talent here in Europe, which provides a really unique opportunity to be at the forefront of something that would be major for the economy going forward. I think what we're maybe lacking over here in Europe, and that's no secret, I think, is the right level of funding and ambition that we do often see in the US. And I think if we're looking at players focusing on Nisk and so on, the US plays a major role there, because the capital was available over there to push those players forward. But I'm still optimistic that if we get our act together over here and provide the capital that is needed, we have the knowledge, the talent, the technology here in Europe to be part of that sort of global elite pushing quantum forward.
When you think of where you will be in, say, 2 to 3 years, so what will universal quantum look like?
Yeah, for us, you'd be looking at a company that will have pushed machines into the market where you can actually come to us and ask the question like, okay, you maybe have X number of qubits here. I'd like to have 10x or 100x, and we can respond with, yeah, we can do that, and this is what we're working on right now. It is that step change and scaling that we must see in this sector as a whole. If you kind of look at how the sort of qubit number and quality of such has increased over the years, it's good, but it's very, very linear, very almost incremental, I would say. And I'm going to get into trouble now by some people for saying that, but with that longer term goal in mind, and if we keep on going the way we are right now, it's going to be tough. And I think we need to see this exponential scaling of high quality qubits, and this is something that our platform will enable. And I think within the next 2 or 3 years, we will have proven that this is that we have a very good answer to that.
In terms of capturing value as a quantum computing company, are you thinking of selling these machines or providing them through some cloud interface, or how do you capture value?
Yeah, it's both. So just for some context for people, what's happening at the moment, that often people make their machines available via the cloud. So you can just access them via your computer. But we're also seeing that there are good reasons for people to actually purchase these machines. So on-prem approach, and we have tapped into that. So the 2 quantum computers we've sold to the German government for 70 million or so a couple of years ago, is really to deliver these machines and put them into their facility. They get the quantum key and we walk away, right? And I think that makes a lot of sense in certain scenarios where people really want to have a local sovereign capability on that and not rely on some machine that's located God knows where, and you know, if you like, you can access it via the cloud. So I think it's a bit of both, and you know, we're doing both, and we have to see how that progresses going forward.
Nice. So we covered really a lot of ground in this conversation. And so one question that I usually ask that is not related to quantum at all is, what kind of advice would you give to a fellow deep tech entrepreneur? Like something you would have loved to have known back then when you started up?
Great question. I'm still on this journey, and I wouldn't want to imply that that I'm all known there. I think one thing, and you know, in particular in deep tech, I think you just keep on going, keep on pushing. You know, it's hard. It's often not quite as short-term sexy as many sort of mainstream investors would love to see. It's hard from a technical perspective. You're pushing things all the time. Now that is something that excites me, and I love that. But it is difficult. It is hard. So you've got to have that conviction, that long-term drive to make that a reality. And I think the other part is that often I think with deep tech is, you know, you've got very technical founders on board. I'm a technical person as well, and we love our tech and we get excited about things that maybe the outside world doesn't quite appreciate or get excited about. So I think a lot of work has to go into finding a way to communicate your technology in a way that people can understand it, that they can get excited around. And I think that's something that we work on very actively, and I would always give that advice to other people to not underestimate that, because what a technical person, what I might find from a physics perspective remarkable and amazing and astounding, some other people might be like, well, who cares? Like, how does it change my life, right? And I think just communicating that in the right way needs a lot of work for a lot of, I think, technical founders.
Are there any tips, tricks, hacks, insights, anything that you really found surprising over the last 2-3 years where you think, oh, someone else should do this actually?
No, nothing comes to mind there. I've been surprised across the board, and one was, if I can, use your question to take a slightly different stab at it, is that I wasn't sure how well the hiring side would go. Right? What we're building, we've got a very heavy engineering approach to this quantum side. We've got way more engineers on board than physicists, which I think is right. But how do you pull away the world's best engineers from the Googles and the Apples of this world to come to this little startup? You can't compete on the salary side and so on, and that really concerned me at the beginning. That turned out not to be a problem at all. I think it really showed that the really smart, passionate people, they want to work at the cutting edge. It's not all about initial money and so on, and they just want to work on something that can really change the world. And we've been able to hire some really, really great people. But that was a worry at first. And I think the second bit was just acknowledging that the founding team comes out of the physics world. We've done a lot in academia to focus on, like, hey, can we really scale this and so on? But you need some smart engineers to look at that. If one is grounded and honest, get some of those guys and have a look at the plans and see if it can really be done. And I was curious what the feedback would be after we've made those hires, and it's been really positive. So I think that those two things, I don't want to say surprising, but still happy it worked out that way and not the other way.
Now, I guess many people, investors, founders, STEM graduates will listen to this podcast, and then who should reach out to you? Like, what are you looking for? Who are you looking for?
I mean, to be honest, we're very heads down at the moment building our tech. We're we're strongly revenue driven, given the sort of contracts that we have. But hey, we would always love to find ways to speak with people who are passionate about what we're building. In particular, people who align with our vision for quantum computing, a longer term mindset, and that sort of appreciation of where we need to go to. And I think we love to have conversations around that. Anyone who wants to work for a really great, exciting, fun startup, please do reach out. We have needs on the talent side, left, right, centre. We're growing quite significantly, and always happy to speak to great talent. And like I said, if investors, etc., are interested, we're not raising right now, but we can most certainly, keep in touch and see how things go.
So everyone, you heard it. If you're excited about quantum computing, please reach out to Sebastian. Man, it was a pleasure talking with you. Thanks a bunch for making this happen.
Thanks so much, Brendan.